Welcome back to Mall 2. Hopefully all of you survived. Unfortunately, we did have some students who couldn't make it. We had more like 170 students who failed. 170. 161. And we did get some students got strong A's, not few, many. I'm still waiting to get the results report. But again, keep challenging the students in terms of if there is a question that was not explained in the lecture and not given to you, we're willing to cancel it. We're up for a challenge, which means everything has been explained. And as I indicated, most of the questions are what we refer to as pseudo scenarios. They're not recommended, but in medical school. However, with your lack of knowledge in terms of clinical knowledge at this stage, we just give it to distract you more than anything else. Most of the questions that you were given are all pseudo scenarios, which means false scenarios, which means it's not like false, it's just at the end you'll see a question in the last statement, the last or before last, where basically we ask you a question. Basically, if I delete, the way you figure it out, if I delete all this introduction and just go to the question, can I answer? And the answer is yes. And that's where students got distracted by. Do expect, hopefully, when you go to the second year or the third year, to get some real scenarios, because as I said, these scenarios are usually discouraged, and we always encourage real scenarios, and which you will see. So, in case you haven't made it, I really think that we still can make it in the summer, because you can take the exam and just hopefully pass and get it over with. If you need any help with Mall 1 or Mall 2, you know where my office is, SG32. I'll be more than happy to help you. That's one. The midterm has been announced, but it's going to be March 22nd, 8 to 10. I just received it yesterday for the mall. And for the final, it's going to be May 2nd. And most likely it will be at 9 o'clock. Most likely. I mean, still we're waiting for the final decision by the administrators, but from what I heard, it could be most likely it's going to be at 9, all the exams, all the finals. But the good thing is that we made 1 week period between your final of mall. The reason we're giving it early, May 2nd, so that you will have 1 week for the renal final to study for. So hopefully we'll do that. For the CBP, your exam is going to be on March 4th, on Monday. We have to move it from Thursday to Monday because we have to cut 1 week because of the fact that we're going to be leaving earlier. We're not, the last day of school for lecture is going to be May 3rd because of Ramadan. So we moved your exam final from Thursday to 2nd to Monday, but also we're going to remove all the lectures, TBL, on Sunday, so that this way you have some time to study for your CVP final exam, or you're going to have the weekend and you're going to have Sunday, so we're going to move the TBL. We're going to post the new schedule, hopefully, in the next couple of days, 3 days. Any question I forgot to mention? Or are you okay? Anyway, is there a relation between Mall 1 Mall 2? The answer is no. We made it in modular form. We made it in modular form so that it is easier for you to not link the two blocks, the two courses. This is why I'm saying, if you haven't done well in Mole 1, you still have a chance. If you could do well in Mole 2, and then you take repeat the exam during the summer, and this way you would be able to make it up. Why? Because, as I said, Mole 2, it's late in terms of concept. As you will see, you had the first module, molecular techniques. It's got nothing to do with what you learned. You're going to be doing some techniques in the lab. Hopefully you already started. Some of you started the lab yesterday, where you're going to do PCR, restriction digestion, electrophoresis, gel electrophoresis. We're going to be doing also, second lab, where we're going to be doing ELISA, and we're going to be doing Western blots as well. So hopefully it will stick. But also my advice to you, study all exams to see the kind of questions to expect, especially in molecular techniques. You have TBLs, and I'm sure that you have the TBL questions, and you have the exam questions. Look into the format, because it's going to be confusing for these two lectures. Enzymes, I tried, this is the first time I teach enzyme here. I mean, I taught in enzymology at my previous post, but this was delivered by my colleagues, and I tried to redo the lectures in a simple manner. I'm getting into high school level. Same material that was covered before, but trying to organize it. So today we're going to be talking about enzymes 1. Tomorrow we're going to talk about enzyme kinetics, enzymes 2, and next week clinical applications of enzymology. Why? Because of the fact that every patient you're going to be seeing is going to be ordering lab tests. You're going to be measuring enzymes. So at least you understand the concept and so on. So, as I said, most of the lectures, I think you have lectures in UPP, you have lectures in your high school about enzymes. Let's just make it as simple as possible. A few things that I'd like you to pay attention to. We're going to be differentiating between zymogen, proenzyme. It's the same word, the same name, whether you call it zymogen or you call it proenzyme. And from the name, give me an example of zymogen, proenzyme. Trypsinogen, chymotrypsinogen, and so on. So it's secreted, synthesized in an inactive form. Why?
So it doesn't
To protect the cell that synthesizes it. Otherwise, it's going to degrade, damage the cell. So it gets synthesized as a precursor. We're going to differentiate between coenzymes, cofactor, prosthetic group, apoenzyme, holoenzyme, and isozymes. These are some terms that I'd like you to know. The isozymes we will learn more tomorrow about. Now, also in terms of objectives, we do expect you to know the function of these catalysts, these enzymes, how do they function, and that is, I just summarized it for you in the second objective where it says lowering the activation energy of reaction. We're going to explain it. But this is the main mechanism of enzymes. At the same time, we're going to discuss the transition state and also propose a rule for this transition state in lowering the activation energy. We will describe classes of enzymes. I'm going to give you the 6 classes of enzymes, and do expect a question. There will be a question right now. I'm going to give you a reaction. You tell me what class is this. As I said, the questions, we're already saying it to you in the lecture, and yet 170 students fail. There's no excuse. We will describe the cofactors, coenzymes, again, and also we're going to describe the models of enzyme catalysis, and the 2 models, lock and key, or key and lock, and also the induced FET as well. And we're going to describe how this would determine the enzyme specificity for the substrate. And now, finally, we're going to be talking about the factors that could be affecting enzyme reactions. Okay, so what are enzymes? Proteins. Are all enzymes proteins?
Yes. No.
Yes. No. Ribozymes. What are ribozymes? RNA that have enzyme activities, right?
Yeah.
So not all enzymes are proteins. At the same time, the catalyst, where they accelerate the reaction without being consumed, and they get recycled. So in terms of recycling, the enzyme would finish the first substrate batch, take it to products,
go again and start with more substrate, so it gets recycled. And they're selected. When I say selected, it means that each enzyme has specific substrate. And we do have three groups, or we have a classification of the selectivity that we will discuss as well. Here's the thing, how do enzymes work? Simple. This is the free energy. We know our beloved dear Gibbs free energy, right? And we know the progress of the reaction. In the absence of enzyme, what do? We have chemicals that we need to react. What do we apply to these chemicals? Heat. Bunsen burner, we just apply heat. Why? To reach the transition state, right there. Once we reach the transition state, this will align the reactants in a better way to react and produce products. Then, free energy drops to this level. Believe it or not, if you add enzymes, you can see that we start from the same free energy for the reactant or substrates. What happens? Instead of applying too much energy, we apply slight energy, and you can see that the reaction would proceed to reach the transition state and then products. Where do we get this energy in our bodies? Right now we have enzymes. Where do we get this energy from?
ATP.
ATP. When we break phosphate groups, we produce energy. But that energy is small compared if you were to, let's say, put someone on top of the Bunsen burner to do some reaction. That's the difference. So what happens is that the enzymes lower what we know as free, or refer to as free energy of activation. This is without enzyme, from here to here, and this is with enzyme. So basically enzymes lower the free energy of activation, as you can see. This is how enzymes work. If you look into the active site of an enzyme, this is the enzyme 3D image of, in this case, this is what we have, DNA polymerase. This is the enzyme 3D structure. I understand most people get terrified by these structures. These are easy structures to draw. You can just Google 3D structures to feed the amino acids, and it will give you these structures. It's really simple. It just represents the alpha helices, the beta plates, plate sheets, and so on. So don't get scared by these three. The whole idea I'm showing to you, because I just want to show you in reality, this is the DNA polymerase. You can see there's an active site right here. And this is how we model every protein. Right now we're getting into virtual modeling, meaning why should we, when we come up with a drug or inhibitor for a certain enzyme, we could screen millions and millions of compounds to see which compound is going to come and block the active site of certain enzyme. But right now we have software, and we have all the libraries of chemicals, and the software automatically will identify the chemical that could fit easily into the active site and say, this could be an inhibitor for this enzyme. It's all virtual, basically, experimentation. And these people are smart people, and believe me, they get a lot of money. I know that a couple of my colleagues make around $250,000 a year just by modeling this system. It's really state-of-the-art pharmaceutical companies. I mean, I'm talking about the crystal structure of the protein. It used to cost around $250,000, and this is to come up with the crystal structure so that we can see the 3D structure of it, so we can fit an inhibitor into it, to understand the mechanism. It doesn't happen right now, it's all virtual. You want a drug, tell me the enzyme, and these people could model for you and see the active site and see, because they have a library of millions and millions of chemicals, see which one would fit into that active site. This is how amazing it is. Anyway, the bottom line, we have substrate that binds to the enzyme at the active site, and then we have the product. So how would you define the active site? If I would ask you, what is the active site of an enzyme?
It's the place in the enzyme where when the substrate is bind, it becomes more active or less active.
It's a place where a substrate binds. Why would the enzyme become less active?
Because
I mean, you said it's simple. It's a site for binding of substrate. But also, it provides the environment for the reaction to proceed. That's how you look at it. So it provides, the active site provides the environment for the reaction to proceed. So this is the definition of active site of the enzyme. Now, if you look into the reaction, if we have reactants, these reactants would reach to what is known as transition state, the T right there. And then this transition state then ends up as products. Basically, this is the same figure where you can see this is without enzyme, this is with enzyme, right? And you can see that we're reaching transition state by applying some heat. This would cause the alignment of the reactant to produce products. And you can see here that in terms of the delta G, when I say no effect on the delta G's of the reaction, why? This is free energy. What's the delta G? Products, free energy minus reactants. But we're starting from both. Between no catalyst with catalyst, if you subtract A from B, it's the same. Right? So there's no effect on the delta G. This is what we refer to, why I made that statement. Now, if you look into the reaction, we have enzyme, active site, we have the substrate, molecule 1 in this case. It forms what we refer to as ES, enzyme substrate complex. Then we have EP, enzyme product complex, and then we have the enzyme releasing the products. The question is, where do you think the transition state is in this diagram? I told you about the transition state here.
Yes.
Is it ES or EP?
Yes.
Or both? Both. Right? Because still, I mean, this reaction is so quick. And there will be products attached to the enzyme. This is the transition state. I mean, this is the initial transition state. And then this is at the end. Towards the end, you have the EP, and then you have the release. So this is basically how enzymes exert their effect. You can see that they increase the products by two mechanisms. By lowering the energy barrier, and this is lowering the activation energy. At the same time, by increasing what we call the favorable orientation of colliding reactant molecules, or in other words, stabilize the transition state intermediate. This is the mechanism of enzymes. So two mechanisms. Lowering the activation energy, and by stabilizing transition state. Okay, we talked about enzyme specificity. Enzymes can be classified in terms of specificity into three groups. The absolute, group, linkage. What's the difference? And I will be giving you examples. Say, what do you think this is? So, what is absolute? It says catalyze one type of reaction for a single substrate. Meaning, example, urease, when it reacts with water, hydrolysis. Right? Urease reacts with urea, hydrolysis of urea is catalyzed by urease. Okay? And this is what we refer to as absolute, which means can urease hydrolyze other substances? No. Why? What's the model you think would fit into this model? Do you think the Kian-Lock or the induced? Kian-Lock. This is how we make it specific for urea. Kian-Lock. It matches perfectly. You take the second group, where basically in the second group, we have this specificity basically where these enzymes catalyze one type of reaction for similar substrate. I gave you an example, hexokinase. What is hexokinase? What's the difference between hexokinase and glucokinase? Glucokinase, where is it present? Liver. Hexokinase? All tissues. What do you think hexokinase can do? Can just do only glucose, or can do all carbohydrates with 6 carbon molecules? Why? Similar structure. Carbohydrate with 6 carbon molecules, they have similar structure. As a result, which model do you think would fit into here?
Induced fit.
Induced fit, or do you think it is the kill-lock?
Induced fit.
Induced fit. The induced fit allows this kind of what we call group specificity, where, for instance, hexokinase can do all hexoses. Then we have the linkage specificity. And I gave you an example. And this is chymotrypsin. Chymotrypsin, is it zymogen, or do you think this is activated form? Activated. So, what do you think? What does it do? Well, it says right there, it catalyzes hydrolysis of peptide bonds between all proteins, irrespective of what protein. There is a peptide bond, it's going to cleave it, irrespective of which protein. So this is why it just, what we call linkage specificity. Are we clear about this? So how do enzymes act? Well, formation of what we refer to as ES complex, enzyme substrate complex. Without enzymes, you can see that we have here a rod, this is just analogy, where it gets bent, basically, to finally produce products. This is without any enzyme. However, with enzymes, in this case, do you think this is kill-lock or induced fit? This is kill-lock. Look at the substrate, fits perfectly to the enzyme. Right? Here we have induced fit. So basically, all what it is, it does the same. What we call it stabilizes the transition state by forming. First of all, it forms this ES complex and stabilizes the transition state to have the final product. Okay, 6 major classes of enzymes. I know that this is going to be a problem for most of you. Let's make it as simple as possible. Why do we need to know this? I'm not going to get into deep, like really, like so many reactions and so on. I want you to understand the concept. Why? Because you're going to be dealing with so many pathways where we say mutase, isomerase, where we say liases. And what does it do? Ligases, what does it do? We just want you to understand the general concept of these. In the exam, I'm saying it right now. I will give you a reaction and say, tell me which class is this. As simple as this. How can we make it simple so that everyone would be able to figure this question out? Let's see. First one, oxidoreductase. And from the name, we have oxidation, we have reduction. If I ask you now, what is oxidation, would you be able to answer? Okay, I'll say it again. I learned this when I was 14 years old from my chemistry teacher. And I still remember it this way. Oxidizing agent. Oxidizing agent gives oxygen